Hello, ladies and gentlemen. My name is Zhichuang Zhang. I am very pleased to be here to join this conference. The topic of my presentation is 3D detection based on camera and LiDAR. The main focus point of my research is the feature fusion method of camera and LiDAR. The outline of my talk as follows. My presentation will include these three parts. First, some background information and the motivation about this research. Second, the main works we have done. Last, some conclusions we have got and future works we plan to do. As shown in Figure 1, the existing camera and LiDAR feature fusion methods can be divided into point-based fusion and bullseye view voxel-based fusion, respectively called point fusion and voxel fusion. They perform feature fusion through point projection and voxel projection. The regions of point projection are still points. The regions of bullseye view voxel projection are small in the distance. The two fusion methods are all affected by the sparsity of point clouds, resulting in the loss of some image information. We found that the size of the perspective voxel gradually increases with distance, which can counteract the effects of perspective projection. Also, it's accurate to perform feature fusion on point level, and it's better to do object detection on the bullseye view. As shown in Figure 2, we use perspective voxel projection to obtain the semantic information corresponding to each point, and then fuse it with the geometric information of each point. Then use the fused information to do object detection on the bullseye view. We name our method Point-Voxel fusion. We build a multimodal object detection framework based on fusion. The framework contains four parts: image branch, point cloud branch, feature fusion module, and the detection network. We use APN to extract multi-layer image feature maps, use PointNet to extract local geometric features of points, and then use our fusion module to perform feature fusion. The fused features are then passed into the detection network to achieve 3D object detection. For image branch, we added ResNet 50 with a feature pyramid structure to enhance the expression ability of each feature map, and then unified the channel numbers of 5 maps to 256 through a lateral convolution. In order to improve the feature extraction performance of the module, we load the weight pre-trained on the Coco dataset for ResNet 50, and then fine-tune on the experimental dataset in advance to obtain the initial weight of the module. For point cloud branch, we adopt a dynamic voxelization to avoid downsampling of the point cloud during voxelization and preserve the complete point cloud data. Two hash tables are built to record the bidirectional association of each voxel with its internal points. After voxelizing the point cloud, a single layer PointNet network is used to extract the geometric features of each point in each voxel. When the module needs all the points in each voxel or the voxel corresponding to each point, the two hash tables can be queried. In the end, we will get 64-dimensional local geometric features for each point. As shown in the Figure 6, PFuse module contains three parts: perspective voxel projection, the semantic feature extraction, and the weighted feature fusion. The corresponding perspective voxel of the point is then projected onto the feature maps to obtain the regions of interest. The semantic features are extracted by our line. And after concatenation and the dimension reduction, the semantic features of the perspective voxel can be obtained. Finally, the semantic feature is weighted and then stated with the geometric feature of the point. To ensure that each point is at the center of a separate voxel, we set the angular interval of the perspective voxel according to the LiDAR resolution and set a small length. For simplicity, we project the four corners of the section where the point is located instead of the 8 corners of the perspective voxel. We first obtain the four sides of the section and then get the four corners of the section. Finally, we project the corners onto the image feature maps to obtain regions of interest. To reduce the quantization errors, we use our line to extract the semantic feature of the RY. We extract a 56-dimensional feature vector from each feature map and concatenate the image features obtained from all feature maps. Then a free connected layer is used for dimension reduction, and the obtained 64-dimension feature is used as the semantic feature of the perspective voxel. Considering that the image is challenged by illumination and occlusion, the extracted semantic feature may have interference. We utilize geometric features and semantic features to obtain the weight of semantic features. We process the concatenated features with a free connected layer and then normalize the values to 0 and 1 with the sigmoid function to get the weight map. We concatenate the weighted semantic feature with the geometric feature, and we get a 128-dimensional fusion feature. After obtaining the fused features, we use max pooling to aggregate the features within each both eye view voxel, and then use the second network for 3D object detection. That is to say, we first obtain the feature map on the bird's eye view and then perform the task of object classification, box regression, and direction classification so as to achieve 3D object detection. During training model, we adopt ground truth-based data augmentation. Ground truth-based can significantly improve the performance of detection models, but this method is not suitable for multimodal because of occlusion. To solve the occlusion, we paste all objects by distance from far to near in images and point clouds. Besides, we filter the points that all objects occlude and the points that occlude all objects. The detailed occlusion point filtering method is shown in algorithm 1. We perform some experiments on the KT dataset. The evaluation results on the KT validation and the test set are shown in Table 1 and Table 2. Despite a single model for all classes, our method achieves competitive performance against other methods that use ensemble detectors. On the car detection, the proposed method is slightly second to FCOMNet on the validation set and the test set. On the pedestrian detection, the results of our method are notably higher than other multimodal methods on the validation and the test set. The difference between fusion methods is the difference between projected regions of spatial units. We analyze the projection results of different spatial units by comparing the sizes of the projection regions. We select 6 projections P1 to P6 whose distance becomes farther in turn. As shown in Table 3, the point projection region is too small, and the voxel projection region is large near and small far. If the region is too large, background information will interfere, and if the region is too small, some information will be lost. Only the projection region of perspective voxel is moderate in size and not affected by distance, indicating that perspective voxel projection can obtain accurate and complete semantic information. We compare PV fusion with point fusion and voxel fusion on KT validation set. The quantitative results are shown in the table 4. It can be seen that the results of 3 fusion methods are similar in car detection. However, fusion outperforms the other 2 methods by 3.6 in pedestrian detection. We also visualize some detection results of different methods. A cyclist and a car are missed by methods based on point fusion and voxel fusion due to 2 field points. Although they are not labeled, they can still be clearly seen in the image. The method based on PV fusion can obtain richer semantic information, so it can successfully detect 2 objects. According to the above experiments, we can get the following conclusions. The existing fusion methods based on point projection or bird's-eye-view voxel projection have the problem of image information loss. Dividing perspective voxels according to LiDAR resolution and performing point-level feature fusions through perspective voxel projection can more effectively utilizing the semantic information. Our future works mainly consist of 2 aspects. The less lines of LiDAR, the more serious the information loss of the existing fusion method. The effect of our proposed fusion method should be more significant. We will verify the effect of our method when the camera is filled with the field line LiDAR later. Our method is still a fusion method which is dominated by the point cloud and cannot solve the problem of information loss caused by missing points. We will focus on reducing the dominance of point cloud and increase the weight of images so as to further improve the 3D object detection accuracy, especially for small dimensional objects. That's all. Thank you. If you have any questions or feedback, you can send us an email.